Oh, we're live. Okay. I just posted the link, so hopefully you guys will start joining. I have a few things I'm just closing out while I'm waiting. So this is for the Electrochem unit test, and you guys, I'm hoping it's been a pretty busy day, so I was not able to get on and post any questions. So I'm hoping you guys will show up with questions. And of course, it's Monday, so we weren't going to do it on Saturday night. That was not going to happen. Usually I like to give it a day in between, but sorry about that. So we're going to do that, and then so we have that test on Monday. And then we're going to review, and I'll explain more. We'll probably have like 3 or 4 classes of review for the final exam. And that's going to be 2 days. We're going to do the free response first and the multiple choice second. And then I believe we have plus on the same day. And so it should be all graded by plus period. So we'll be able to have the plus period to go over your final exam, which would be really nice to see that score before you take the AP exam on Monday. All right. Sorry. Okay. So I guess I could start with something. I'm trying to review with you guys, but you guys need to post questions as soon as you can. And I have the Electrochem practice test. I'm not sure about lecture 21 and 22, but I would be happy to go over those. The nice thing is that there are solutions to that are already posted, I believe. Okay. So, oops. Oh my goodness, I've maxed out my Bamboo tablet. All right, if you guys would just give me a second. I have to delete a file in order to do that. I didn't realize we were already that far. Let me see if I have anything from last semester. Okay. Okay, let's see what we got. Graph paper. Okay, this is much longer to be waiting to start something. You guys need to come up with something though, please. The sooner the better. Oh, good. Aria, way to come through, buddy. It says can you do number 1 and 2 on the practice test? So I'm going to assume you are referring to the multiple choice. So let's see. All right. Then let's show those first. Just show them. Then take a look at them. We can go from there. Okay. Oh, good ones. Yes, good choice. All right. So if 0.060 Faraday is passed through an electrolytic cell containing a solution of indium 3+ ions, the maximum number of moles of indium that could be deposited at the cathode is, and why is it B? So that's a good question. So let's take a look. Oops. And so now we'll go to the Bamboo paper. Okay. All right. So, all right, multiple choice number 1. And in doing this, 0 Faraday. Okay. So it's going to be important to know the reference sheets. And let me Being the brilliant person I am, I didn't bring those up. Maybe I don't have to actually show the whole thing. Let's see. Maybe I'll just write this stuff down so that you can see it. I'm not going to keep going back to the reference sheet. I think that's going to take too long. So so for this, it's important to know some detailed information. I equals Q over T, all right? And in this place, Q is, so I is amps. So amps equals coulombs, which is charge, over time, which is seconds, okay? And that's kind of interesting. I don't know if it's going to relate to this one because we're really looking for, what was the question again? The question was the maximum number of moles. Okay. And so I don't know if we're going to need that one so much. Another one that you should be aware of, though, is the Faraday's constant. F is equal to 96,485 coulombs per mole of electrons. Okay. So really, that's 1 mole of electron. 1 Faraday is 1 mole of electron, basically. Like, that's the number of coulombs, but really, I mean, what we're looking at is this mole of electrons. Okay, so now because this is multiple choice, you can't use your calculator. So this is actually not too bad. So when if it's looking for time, if it's looking for coulombs or joules potentially, you know that you're going to be using this equation, okay, which is going to end up including this number, okay? But if we're using Faraday's and they're looking for moles, you're kind of going to be using this right here, all right? So you have 0.060 Faraday's, all right? And if you do that, make a little bridge, and for every 1 Faraday, you have 1 mole of electrons, okay? And for every 3 moles of electrons, you have 1 mole of indium 3 plus, okay? So the key is that 3 plus right there. So then what you end up with is 0.060 divided by 3. And that equals 0.020 moles of indium 3 plus. Because the Faraday's cancel, the moles of electrons cancel, leaving you with that. So there's your answer. So that's the answer to number 1. All right, now we're going to look at number 2. All right. You have zinc plus the copper ion yields the zinc ion plus copper solid. So we have an electrolytic cell. So this is, again, it's electrolytic. You're pushing current. You are using like a battery or something to push current again. So this electrolytic cell has that reaction. The observed voltage was found to be 1 volt instead of the standard cell potential E naught of 1.10 volts. Which of the following could correctly account for this observation? Okay, so we have a few things going on here. Let's set up the cell so that you guys can see that. I think that would be easier or more helpful. Okay, so let's go over here. This is multiple choice number 2. And we have this formula, zinc solid plus copper 2 plus, which of course is aqueous, goes to zinc 2 plus, which is aqueous, plus copper solid. So really, you look at this, you have zinc, which is solid, going to, zinc 2 plus plus 2 electrons, and you have copper 2 plus plus 2 electrons goes to copper solid. Okay, so this is your oxidation. Oxidation is loss, you're losing electrons. This is your reduction. Reduction is gaining, you're gaining electrons. Oxidation happens at the anode, okay, because they both have vowels here. And reduction happens at the cathode because they both have consonants. So let me just highlight a few things actually. So anode happens at the, or oxidation happens at the anode. Reduction happens at the cathode. You've got this electron being gained, why is reduction? You have these electrons being lost, which is why that's oxidation. Okay, so if we have our cells here, and remember, this is an electrolytic cell. Okay, oops, let me, okay, so there's probably a salt bridge here. Okay, and then there is a plate here. Okay, and maybe since this is the anode, this is zinc. This is your battery. It's like they usually, maybe I should do that. I don't really know how to represent it really well. I'm not really good at the physics side of it, but okay. And then this is your copper. And this is happening at the cathode. Okay. And we'll put some solution in here. Right. So again, copper and zinc. And we've got some zinc 2 plus in here that's coming off. And we have some copper 2 plus, which is going on here. And we've got the electrons, and they are flowing this way. Okay. All right. And cathode is got a T in it, which is like a plus, which is, so this is positive. And anodes, well, we just know this is negative because it has more electrons. It's giving up the electrons. Okay. Now the question says again that the observed voltage was supposed to be 1 instead of the 1.10. Okay. And what could account for that? All right. So remember that this, I'm going to write this down here again. This is a reaction that can be subject to Le Chatelier's principle, because that keeps coming back. You guys need to be really familiar with that. Okay. Now, with Le Chatelier's principle, something to be aware of is that, or just even equilibrium, because that's a part of it, solids do not play a part. Okay? Solids do not play a part. So technically, these solids do not play a part, right? So the first choice there, the A choice, was the copper electrode was larger than the zinc electrode. Copper was bigger than zinc. Well, it doesn't matter, right? Products over reactants, zinc 2 plus over copper 2 plus, right? There's nothing involved. Like there's no pushing this reaction, nothing like that's happening. And so it can't be A, all right? C, a brown color will appear in the solution near the negative electrode. Now, this is our negative electrode right here. So brown would somehow indicate that maybe there's a precipitate happening in there. Maybe the zinc is combining with something in there as it's coming off. It's forming a precipitate, right? Which means that the amount of zinc that's in solution, if it's forming a precipitate, then that would be pulling it away, which would speed this reaction up, which would force it to the right. If it forced it to the right, that means it would happen more, and that means that the voltage would go up. So that can't be it. D, the salt bridge contained KCl as an electrolyte. Well, that really doesn't matter, honestly. if you have KCl in here, you have K plus and Cl minus, and the K pluses, the pluses are going to go over here, and the Cl minuses are going to end up going over here, and you're going to end up with, to get it balanced, and it's doesn't matter at all. It doesn't affect it. Now, B, the zinc 2 plus solution, which is right here, was more concentrated than the copper 2 plus solution, which is right here. So you're saying that this, let's see, zinc 2 plus is less than copper 2 plus, okay? And that means if the reactant, I'm sorry, the products are, wait, did I say that right? More concentrated, oops, sorry, I did that wrong. It's more concentrated, there we go. Is more concentrated, so that's a higher number. So K would be a higher number, so it wants to go this direction. It's going to resist. If we add more, it's like our balancing act. If there's more on the zinc side than the copper side, it's going to want to go backwards and reverse to get back to equilibrium. And so that's going to lower the voltage for sure. Okay, so that's why B is the right answer. Okay, so I did a lot of extra things here, but I did a lot of extra things to try to help with your understanding of the cells and how they're working. Because of course, that's a lot of what this test is. Okay, sorry, I had to get a drink of water. I'm starting to get dry. So that is number 1 and number 2 on the practice test. Good. All right, Mary, could you please review multiple choice number 12 and for response 2A? No problem. So let's look at multiple choice number 12. Okay. All right, 12. You've got some, so you've got G plus chromium 3 plus yields 3 of the G2 plus 2 RCr. Okay, so what you have here is this right here, the top one, that is the E kind of total, we'll call it. That's the E of the whole cell, the final cell. This one right here, this second one, is a half reaction. Okay, so if this is a half reaction, this plus something else is going to give you 1.93. So the question is, how do you know which one to pick? So let's go ahead and, again, let's do the bamboo tablet. All right. All right, multiple choice, number 12. And I'm gonna write these out again, but I'm gonna write them in a different form so it kind of helps you see. Oops, you know, I didn't give myself enough space. All right, so 3G, no, didn't give myself enough again. Oh my goodness. 3G as a solid plus 2 Cr3 plus, which is aqueous, goes to 3G2 plus, which is aqueous, plus 2 Cr solid. Okay, now what you need to figure out, this is kind of like Hess's law again. You're adding these things up to see what you need to have. Now it says that one of the equations is the Cr3 plus going to plus 3 electrons. All right, so I see a Cr3 plus here, so I know that my Cr3 plus is on the left, plus the 3 electrons goes to Cr solid, which is great because the Cr solid's right here, Cr solid right there. In fact, what I'm going to do is I'm going to use different colors here. So the Cr3 plus is here, and the Cr solid, sorry, Cr solid's there, Cr solid, and Cr3 plus is here, and Cr3 plus is here. Now, it doesn't really matter about the coefficients because when you're dealing with the E of the cell, coefficients do not matter. That's a big difference, okay? All right, so now what we're looking for is this one right here, the G solid, and it's going to G 2 plus 2 electrons, okay? Now, our E of this one is equal to negative 0.74 volts. And it's already written in the reduction form, okay? The E of this one, we don't know, and the E final is equal to negative 0.74 volts. Now, the thing is, if you remember, that a lot of times an equation is written in the reduction form. And actually, let's go back just so I can show you again. When you're doing these calculations, you'll notice that it says determine the standard half cell reduction potential. Reduction. Let me give that a little extra boost. Where's my bold? Bold. Give it a little like red. Reduction. This is the reduction potential. If it's the reduction, then you've got to write it, or when you get the number, it needs to be in the reduction form. Okay? And so here it is. This is the reduction form. But we recognize that if we go back to our rule paper, that if we add these together properly, it gives us a, oops, I wrote that wrong, didn't I? That 1.93. You guys are probably sitting at home going, Mr. Werner, you messed that up. E equals 1.93. Okay. So what that means is, and when you're doing this, you can do two ways. Remember that the E of the, why am I forgetting this all of a sudden? E of the cathode plus E at the anode equals the E naught, these are knots, E naught total, or the final, okay? Or you can say E naught of the reduction at the cathode minus E naught reduction at the anode equals E total for the cell, okay? And you'll notice that the difference is that this one is an oxidation number because this is E naught of the oxidation. This one is reduction, okay? And so you'll notice that the difference is that when they kept them as reductions, there was a minus. But if it was just, basically, if it was just reduction minus oxidation, or reduction and oxidation, then it's a plus, okay? So when we look at this, we just, whatever this number is, well, what number plus negative 0.74, negative 0.74 is going to equal to 1.93. And because it's written in the, I feel like I'm doing this wrong. It's supposed to be the, oh, I know what the problem is. Sorry. I hadn't actually gone through this problem before. This would not be right. So something is wrong in there. So, okay, let me just take a look at this for a second. What should have happened is that some number plus negative 0.74 is 1.93, which means that it would need to be, it would be like a math problem. 1.93 equals negative 0.74 plus x. And so that's going to be plus 0.74. So this should have been 2.67 is equal to x, which really is equal to E naught of the oxidation. Oh, I think that when we did the numbers and typed them up, I was wrong. So what happens is if that's the oxidation and they want the reduction, then it should have been negative 2.67 to get the answer. And so it had D down there. Sorry about that. This number, so let's go take a look at these. 1.67, where did that come from? So let's go back to this right here. So I would say that this should have been one or the other. So that's why it's negative 2.67. So sorry about that. But that's how you solve that one. That would be a good thing to know because there'll probably be something like that on the test. All right, for response 2A. So there's 1A, and here's 2A. So I'm assuming it's this one right here. Just be a lot easier if we did it like this. Okay, I might have to go back to the Word document. I changed it into Google, and I think it messed up the text is overlapping itself. Let me see if I can pull up the original real quick. All right. Oh, good. All right, I have it. Okay, let me close this one out then. That's not going to do us any good. And all right. There we go. All right, I think it'll be easier to see this way. Okay, good, there we go. Much better. So a solution of this unknown metal, nitrate, is electrolyzed when a constant current of 2.5 amps is applied for 35 minutes. 3.06 grams of the metal is metal M is deposited. Calculate the molar mass of M and identify the metal. So I'm gonna guess you must have seen some sort of error or something in this because it looks pretty well explained. Well, we'll go through it. All right. Let's go to the next page. All right, now this goes back to that I equals Q over T, which very useful here. So this is number 2A on the free response. Okay, so we have 2.50. Oh my goodness. 2.50 amps. We have 35.0 minutes. And we end up with 3.06 grams of the metal. So we want to know the molar mass of this unknown metal. All right, and if you guys remember, I equals Q over T, which is the amps are equal to the coulombs. You know, we'll just do a big C. I'm not choosing a big. Over seconds, okay? And then a Faraday, 1 Faraday equals 96,500 over 1 mole of electrons, coulombs, sorry, 96,500 coulombs over 1 mole of electrons. Okay, so what we need to do is we need to get this converted into moles as quickly as possible, or as easily as possible. And it looks to me like if we go to coulombs, and then we can take coulombs to moles of electrons. something like that. So if we have, because coulombs is equal to amps times seconds, okay? We had 2.50 amps, all right? Let's make a bridge here. And for this one right here, if we have, oh, we did the amps right here. And we could do it like this. Oops. I'm trying to think of the easiest way to do this, which means that I'm struggling with showing this to you. Okay. 96,000. We need to cancel out the amps is what we need to do. I'm trying to say how we can cancel out the units. So I can see, I'm trying to look at it, see the answer, see where it was tripping you up. And I would say this, that if you have 2.50 amps, if you remember this, and it's, so for every 1 amp, right? 1 amp second, you get 1 coulomb. We'll do it like that. So you can see how the units cancel. So because remember, this is amps, coulomb seconds. 1 amp second is 1 coulomb. And for every 96,500 coulombs, you get 1 mole of electrons. Can you see that, how that worked? So here we have coulombs, amp seconds, all right? And so this is a conversion factor we just put into here, okay? And these are equal to each other, and they're already a conversion factor, and we just flipped it over and put it here, okay? All right. Then for every it was a because it was MnO3 2, which meant the M was a 2 plus, okay? And for every 2 moles of electrons, you have for every 2 moles of electrons, you get 1 mole of whatever that metal is, M, okay? All right. And the seconds are over here. Okay. And then to continue this on a little bit, because we get the coulombs, moles, this is moles of electrons. Then we also want to multiply times seconds. And we have, for every 60 seconds, we have 1 minute, and we have 35 minutes, okay? So what happens is that, so let's see, to try to draw all this, this 2 plus, this is right here, okay? And the 35 minutes, just go around to this, all right? Which, makes all sense with that. Now, canceling out units, the amps cancel with the amps, coulombs cancel with the coulombs, the seconds cancel with the seconds, the moles of electrons cancel with the moles of electrons, the minutes cancel with the minutes, leaving you with moles of M, okay? Once you plug all that in, you end up with 2.72 times 10 to the negative 2 moles. And what I'll do is, just in case that was part of your question, was to make sure all the numbers came out, I'll go ahead and plug that in just to make sure. 2.5 divided by 96,500 divided by 2 and times 60 times 35. And yeah, that's what I got. 2.72 times 10 to the negative 2 moles of M. Okay. Now to get the molar mass, remember that gave us 3.06 grams, and molar mass, Tim, is grams per mole. So molar mass is equal to 3.06 grams divided by 2.72 times 10 to the negative 2 moles. And that should be equal to 3.06 divided by 2.72, exponent, negative 2, and I get 112.5 grams per mole. And when I look in the periodic table for that mass, 112.411 is cadmium. So cadmium is 112.41. So cadmium is our answer. Oh. All right. So I kind of went the long way on that one, but I really wanted to make sure that you could see how all the units canceled out and how they were equivalent, each of the steps. You really want to walk through that. Like, how can I get these to all cancel out? Okay, and so I believe that answers Mary's questions. Okay, so the next one that I saw a second ago is, I think I saw Ephraim's. Could you go over 2B and 2D, which actually works really well with this since we just finished 2A. All right, so once we have the cadmium, the metal identified in A is used with zinc. Write the net ionic equation for the cell and calculate the cell potential. So you would need to use a table for this. And remember that on the test, I'm going to provide you all the numbers you need. Not a test for, not the whole reduction potential table, but rather I'll give you the ones that you need. Like, I'll give you 3 or 4, and I'll give them to you in just the reduction form, and then you'll have to determine which one you should put oxidation and such, okay? So here's the galvanic cell, which means it's creating its own current. It has a salt bridge. It has this unknown metal M, which we've determined to be cadmium, and there's the zinc. They're both, oh no, they're not both in nitrate. The cadmium's in nitrate, the zinc is in sulfate. So that is interesting. Okay, so let's go ahead and take a look at this on the bamboo tablet. All right. So right now we're on 2B. Oops, I don't like doing that. All right. Response 2B. And so what this question is asking for again is the net ionic equation. All right. So let's take a look at something real quick. All right. So let's see. So we've got two potential reactions. If we put them in the reduction form, zinc plus 2 electrons gives you zinc 2 plus and cadmium 2 plus. Wait, I did that wrong. Not sure where my head is. Zinc 2 plus 2 electrons gives us zinc as a solid. Cadmium 2 plus 2 electrons gives us cadmium as a solid. Okay, so now we just need to look those up. So let me pull up a table, reduction potential. It's probably in your book too. See if I can find one that's pretty visible. I think I may have found one. Let me just double check that there's cadmium on it. Cadmium, not real common on these tables. There it is. We got it. Okay. So we want to compare them. Remember that, goodness. Remember that whichever half reaction is higher is the reduction one. Okay. So we're comparing cadmium and zinc. And cadmium is right here. Cd2 plus 2 electrons gives you the negative 0.40. All right. And if we find zinc, we see it a little bit lower. Zinc 2 plus 2 electrons gives you zinc. So what I would say from this is that since the cadmium is higher, that's the reduction that's actually happening. And the zinc 2 plus is lower, so that's the oxidation half reaction. Okay. So let me go back and share the bamboo tablet. There we go. All right. So the cadmium's like this, and so the zinc is not like that. The zinc will be like this. Zinc as a solid goes to zinc 2 plus 2 electrons, which means that its sign is reversed. So cadmium gets to say its E naught is equal to negative 0.40 volts. And we would flip the sign on this one, so it becomes positive 0.76 volts. And we're going to add them together, and we come out. Remember that the 2 electrons cancel on each side. We end up with cadmium 2 plus zinc as a solid gives us cadmium as a solid plus zinc 2 plus. And remember, since we flipped the sign, we can just add them together. So negative 0.40 plus positive 0.76 means that our E final, our E total, is 0.36 volts. And that, my friends, is the answer to 2B. Okay, now we're on to 2D. Oh, I don't even see a 2D. What the heck? Did I read that right? 2B and 2D. So, gosh, I'm not sure which one you guys are looking at. Oh, that should be the one that should be the one that I handed out in class. But did I, I don't know what happened. So I'll just pretend like you meant to say E, or that I somehow typed it up wrong. So we're just gonna go, oh, Ephraim, you meant 3D. Okay, sounds good. So I'll finish that one and say done. And I'll select your 3D and 3. One, two. You see this one, calculate the standard free energy change delta G in this electrolytic cell. All right. All right, since I already pictures, let's go ahead and do it. It's like a whole big one though. So let's just do it. Make it happen. Let me show the document real quick so you guys can see what I'm looking at. All right. So I'm probably a little confused. This was supposed to be 3 right here. So this is, I guess, A, B, C, and D. And D is the calculated standard free energy change, delta G naught, in this electrolytic cell. Include your units with your answer. God, Gosh, let me go back and see. I feel like I did something different with it. I feel like I did something different with the test. All right, guys, just hold on a second and see what you guys are looking at. If it's the same as what I'm looking at. I apologize for the delay here. I have to go into my email at school, and it froze on me, so I wasn't able to, it closed, and so I have to go in right now. Where is it? All right. Practice test, Electrochem 1415. Maybe I just opened it up, or I just changed it. Two, A, B, C, E, 3. Oh, I did. Oh, I totally, no. Oh, no, that's fine. Okay. Okay, so it's dependent upon, I gotcha. Thank you for waiting for me, guys. All right, so so we are talking about the same one. I just gave it different letters, but the question's the same. So the standard for energy change in that one. So we, of course, need to identify what's happening at the cathode and the anode. So this is going to be a long question. And if we go past 9 o'clock, we go past 9 o'clock. You guys don't have to stay on, but I will stay on and finish all the questions you guys have answered. Okay. All right. Let's go to the next page. 3D. All right. So what was happening here is that you had an electrolytic cell, which means you have to apply current. And this was the big thing I did right before. I did it in class to try to get you prepared for some of this. So you've got Fe iodide. It's Fe2, which means that it's FeI2, right? Iron 2 iodide. And so it's aqueous because it says a solution of that. It didn't say molten, because that is, of course, a ionic bond. It just said a solution. So it's in water. That's the key thing here. And so you're looking at it, and you've got some possibilities. You've got Fe. These are the reductions that you could have. Oh, I'm sorry, oxidations are first. So the first one is the oxidation half reaction. So oxidation half reaction, it could be Fe goes to Fe2 plus 2 electrons. You can have I going to I, oh, no. Sorry, you're losing electrons, and it's iodine, which means that it's actually I minus goes to I2 plus 2 electrons, because whereas these are metals a lot of times, which are going to lose electrons to form cations, when you have a non-metal, it starts as an anion because it's got to be negatively charged to lose electrons to get to its neutral state, we'll say, which is diatomic in this case. Now, other options might be, you could have water. And if we remember those, H2O, and so H2O going to its, if you're having an oxidation, so it's going to go to O2 plus OH minus. I believe that's the oxidation. All right. So let's take a quick look at our redox potential table. And so you're looking for oxidation. So it's kind of like whichever one's, well, the reduction happens, it's whichever one's highest. Let's just take a look. So where's iron and water and iodine? So here's iodine, and it's I2 plus 2 electrons yields 2I minus, because you have multiple things to choose from here. So that's in the reduction form. Oh, there's Fe3 plus. Where's the Fe2 plus? Here's they're right together. Excuse me. There's the Fe2 plus. And negative, and I'm having a hard time, guys. Sorry. Oh, there's the water. That's not the one we're looking for. That's the H2. That's not the oxidation. All right. So these are all written as reductions. So we need to flip them to, we flip them to oxidation. These are all reductions. We flip them to oxidations. So if we do that, remember we flip the sign, which means that the I minus going to, this has a negative 0.54. Right? So the more positive it is in its reduction form, the more negative it's going to be in the oxidation form. Okay. Now, so that means that let's see, remember that? Yeah. So you have that. So that's going to be iodine is over the iron. Now I will say this, which is kind of interesting that they did this way. I'm wondering if when they said solution, see the solution means it's aqueous, but they didn't refer to the water because the water should be even higher than that. So here's the water. If we flip that one, that would be even more. Is that our, yeah. They did a 4H plus. They must have meant that it was molten, because then their key, they didn't show that. So anyways, they have the iodine. So that's good. So that's a negative. So let's take a look now at the test again. So you can see that the iodine was, when you make an oxidation, is much lower than the iron. And then the reduction in its form would be, would actually have been higher than the iron, because it was, yeah. So the reduction, if this is the reduction, then that's the one that happens at the cathode, okay? Once you have those, then you can get those numbers from that table. All right, so let's take a look for a second. So I need to pick this up a little bit. So the E naught of the cell is and the way they did it is that you can have the E reduction at the cathode minus the E reduction at the anode, or remember, you can do the E reduction, the E at the cathode plus the E at the anode. And the anode one, you just switch. So that's what I prefer doing. So you get the negative 0.44 from the iron, and you get the negative 0.53 from the iodine. And on the table that we looked at, it was 0.54, which is not a big deal. Just use whatever table you're given. And that gave you the negative 0.97 volts. And once you have that, you have the delta G naught is equal to negative NFE. Now that's an equation that you should be able to find on the reference sheet. N is the number of electrons, the moles of electrons that are transferred. And if you look up here, there's 2 moles of electrons from each one. Now, if there was like 2 for one and 3 for the other, you have to find the lowest common factor. in which case the 2 and the 3, they both go into 6. So it would be 6 electrons that we transfer. And you would do that. Remember, because when you are combining the two reactions, you want to make sure that the number of electrons gained and the number of electrons lost are the same. And so anyways, it's really easy for this one because it is 2. So 2 times 96,500 for the F, the Faraday's constant, times the E naught, which is negative 0.97 volts. And that comes out to the 190,000 joules per mole, or it could be 190 kilojoules per mole. Okay. And if we look at that, the E, oh no, you didn't ask that, just for D. Okay, sounds good. All right, the next one that I had seen was from Arya, and I'll start at the top here, select. So for number 13 on the multiple choice. So let's just scoot right back up here. Again, I'm gonna be picking this up a little bit. If 0.5000 Faradays of electric charge pass through a lead to nitrate solution, what mass of lead is plated out? Okay. All right, let's write this out. All right, this is multiple choice number 13. And we have 0.5000 Faradays. And we want to get to the, the grams. Okay. And if you remember that 1 Faraday, let's see, let's go back to that. Wrote some of that. Okay, so yeah, the Faraday is equal to 96,500 coulombs per mole of electrons. Okay, so we're going to end up working our way up through this because we're trying to get to, once we get to coulombs, because we're already at Faraday's, we didn't start with amps. We went straight to coulombs. We can skip. So we're going to actually end up kind of skip because usually you get to the mole of electrons as a Faraday, and you have to use the 96,500. But remember, we're in the multiple choice, which means that we are, since we're in the multiple choice, we're not using this. This is going to be too much. Okay. So, all right. Okay. So we have a Faraday is equal to a mole of electrons. And for every 2 moles of electrons, we have 1 mole of the Pb2 plus. And for every 1 mole of the Pb2 plus, it's 207, we'll say 207 grams, okay? So we do this 0.5 times 207 is basically 3.5, and then 103.5, oh, by the way, the Faraday's cancel, the moles of electrons cancel, the moles of lead 2 cancel. So 103.5 divided by 2, looks like it would give you about 51.75 grams, something like that. And so when you look at your answers, C is closest with 51.84 grams. So that's how you do multiple choice number 13. Oops, I didn't select it to begin with. So that's how we do that one. So number 13, we just covered that one, just have to look back. Okay, and now we're doing, Aria, number 9 and 12 on electron transfer reaction worksheet. You got me. I don't know what the name, I don't recognize that one. Would it be was it like the Chemi Bear, like the 21? Or was it the lecture? I don't know. You're gonna have to be more specific on that one. Come back and ask that too. Give me a different name and I'll try to track it down. Okay, Danielle, Could you explain which condition would skew lab results? Multiple choice 2 and multiple choice 11. Okay. So I did multiple choice 2, so just go back earlier in this one. Watch it later. Oh, I see what you're saying. You want to know, okay. And number 11 is source of deviation. All right, let's do number 11. I can kind of talk about it. So you have this galvanic cell and you've got tin zinc. There's your balanced equation. The voltage is measured at 0.66 volts. However, when it's supposed to, the standard cell is supposed to be 0.62. So why did it change? All right, so let's go to the bamboo tablet. All right, so I'm gonna draw this cell because that's what's gonna help you guys see this. And just to, oops, let me write out all right. And we had tin 2 plus zinc as a solid goes to tin as a solid plus zinc 2 plus, which is aqueous. There's our salt bridge. There's our electrodes. And it was a galvanic cell, which means we can have a voltmeter or something like that. Okay. And if we set it up so that the anode is on this side, oxidation is loss of electrons. That would be the zinc, because the zinc going over this side ends up giving up +2 electrons. That means the tin is over here. This is the cathode. It's gaining electrons. Tin 2 plus 2 electrons gives you the tin here. All right. And so, okay, and it doesn't really matter what we have in there. But the electrons are going this way. That's good. And that means that we have zinc 2 plus coming out into solution. And that means that we have tin 2 plus is going up onto the electrode. Sorry, my throat's getting really dry. Okay. So it's products over reactants, which means it's zinc 2 plus over SN 2 plus. And it's Le Chatelier's, which means, remember, the solids kind of don't play a part. So it's just those two aqueous ions. And it was measured high, but the standard cell, what we expected, was low. So what would push this reaction? So let's just look at that. Let's not even think about the answers. Let's think, what's gonna push this reaction to produce more volts? What's gonna push more electrons across? Okay? So according to Le Chatelier's, if we decrease the zinc 2 plus in some way, that's gonna push the reaction to the product side, which is going to increase our electrons, okay? Let's say we could decrease the zinc 2 plus. We could increase the SN 2 plus, okay? That will also push it and increase our electrons. So any condition, in this particular case, that's going to, because we're trying to increase the E naught. Whatever's going to push the reaction this way, okay? So that could be the addition of SN2 plus, the removal of ZN2 plus. I don't know, that's basically what I'd be looking for. So we want to, we want ZN2 plus to go down and SN2 plus to go up. So whatever conditions do that. It could be, if you could figure out some way to precipitate out the zinc 2 plus, if you added more of a solution of SN2 plus, like S as tin nitrate over here, if you, oh, I don't know, whatever would do that. So let's look at the answers and see which one would be closest to what we need to do. All right, there we go. So A says sulfate was the anion at the anode, and chloride was the anion at the cathode. So our cathode was tin. Tin chloride would actually, let's say that precipitated out. The sulfates are usually pretty soluble. Tin chloride would actually reduce the tin, and we want to increase the tin. So that's not out. B, having zinc less than tin. Well, that's exactly what we wrote. So B is the answer, obviously. The anode had a larger mass than the cathode. Remember that the solids don't matter. They're not a part of that situation. The volume of SN2 plus solution is greater than the volume of the zinc 2 plus solution. Volume doesn't matter, it's concentration. So D can't be right, so B. So I don't know if that helps you at all. I mean, on 2, if we were looking at it, if you remember, so if one was more concentrated than the other. So whatever it would take to make that happen, you have to look at it. You've got to look at your equation. Let me go back to it for a second. There we go. You've got to look at your cell, whatever you're dealing with, and if you want it to be more, then you've got to push it to the cathode side. You've got to push it to get more, a higher concentration, more moles of whatever that ion is that's going to go onto the cathode. If you are trying to figure out how to make there be less voltage, then you need to decrease the ions at the cathode, and you need to increase the ions at the anode. However you want to do that. But that's the conditions that'll change. So that's, and again, it's precipitation, it's addition of concentration or whatever. Sometimes it's just straight, hey, one's more than the other. Okay. All right. How close is this, F-frames, how close is the study guide to the test? It's as close as all the rest of the study guides have been as close. All the study guides are as close to their test as they are usually, I guess. Yeah, that's it. Okay. So are there any other questions? Aria, did you, I don't know which one you were talking about. I don't know which worksheet it was. So if you can figure that out. Of course, you guys can come before school tomorrow. We have a CSF meeting, which starts at 7:15. So you can either show up like 6:45, 7 and ask me questions, or you can wait until after 7:30 when our meeting should be over and ask me questions. But I would prefer you guys not ask me questions between 7:15 and 7:30 while our meeting's going on. And that's all. Let me just take a quick look just to double check. Make sure you can balance. I think it's good that you guys ask questions about running current and plating out metals. That's good because that's on there. Delta G and K, how those are related, that's good. Make sure that you know how to do the bridge, or do the you don't have to draw galvanic cell, but know how to work your way around it, understanding what's going on in there. Understand like the question about when you do it, is the sign of delta G what you would expect it to be? That's going to be in there. Make sure that when it says solution, when I say solution, I'm referring to something being in water. So you need to pay attention to what it is in water, because if we do something like that again, electrolytic cell, it could be water at the anode or the cathode. Yeah, so I guess that's it. Okay. All right, guys. Well, since no other questions popped up there, I think that's it. Get some rest tonight. Come with questions tomorrow if that's what you guys want to do. And I hope you guys had a good weekend. All right, I'll see you tomorrow. Bye.